Hi everyone, my name's Alex Jenkins. I'm a postdoc at the University of Cambridge, and I'm really excited to be giving a talk as part of this tabletop scale cosmology conference. I think it's really exciting to see that there's a growing community of people who are interested in using these types of experiments for learning about cosmology. In my talk, I'm going to be telling you about these three recent papers here, where myself and my collaborators are trying to use these types of tabletop experiments to learn something new about the physics of bubble nucleation or vacuum decay in the early universe. And I'm going to tell you about why that's interesting for cosmology and what these experiments might be able to teach us. So this is work that was done with this great team of collaborators that really is interdisciplinary and brought together, cosmologists, but also people who are interested in cold atom experiments, which is the experimental platform that we want to use. So the plan for the talk is I'm going to start by telling you about what vacuum decay is and why I think it's interesting for cosmology in all kinds of different ways. Then I'll tell you about how we can simulate this process in the laboratory. And then finally, I'll tell you about the theoretical work that I've been doing to try to prepare ourselves for the data that will come from these experiments and see how we'll be able to extract fundamental physics insights from it. So the basic picture for this process of vacuum decay is very simple. We just have a single relativistic scalar field. It obeys this Klein-Gordon equation that I've written here. But in general, this field can be living in an arbitrarily complicated sort of potential landscape. So in particular, it might start off in this kind of local minimum of the potential, but really it wants to get down to the global minimum of the potential down here. So this local minimum for small kind of excursions in the value of the field, it looks like it's a vacuum state, but it's not really because the lowest possible energy state the field can be in is down here in this global minimum. So this one we call the true vacuum, and this starting point we call the false vacuum. And the question is, how does the field escape from the false vacuum and get down to the true vacuum? So in general, it's very difficult to get the entire field everywhere all at once to transition from the false vacuum to the true vacuum. So instead, what tends to happen is a localized region in space will transition first, and this looks like a bubble. And then the bubble will start expanding and gobbling up the surrounding space and converting it into true vacuum. And in general, you can have multiple bubbles forming, and they can collide with each other and give you some interesting dynamics. But this is a very difficult process to try to capture completely theoretically because it involves quantum effects. It's very non-perturbative and non-equilibrium. So it's a very challenging problem in general. So I'm going to show you a simulation video now that just kind of fleshes out some of the things I was just saying. So we see that we start with this blue state, which is a false vacuum, and it's filled with these quantum fluctuations that eventually they interact in some kind of nonlinear way and produce these bubbles. The bubbles expand, they collide with each other. There's a transient phase of kind of complicated dynamics, and then eventually the universe settles down into this true vacuum state, which is shown in red here. So some open questions for this process. There are theoretical tools that have been used for decades to try to describe the rate at which these bubbles form and what the bubbles are expected to look like. But crucially, these methods only really work in imaginary time, so they're Euclidean methods. And this leads some really big questions of, how do I take this Euclidean formalism and interpret it in real time? If I was watching the false vacuum boil and form these bubbles in real time, what would that process look like? And this question becomes particularly sharp in the case where you have other stuff that's happening in your universe. The universe is evolving, there's dynamical things going on. And so we really need to be able to describe the dynamics of this scalar field on top of that in real time. There's also the fact that the usual methods for calculating the decay rate assume a particular symmetry for the bubbles that are nucleated. But in practice, we expect those symmetries to be broken. So for example, if you have multiple bubbles that form, that breaks these symmetries. And so that is then going beyond the kind of standard formalism that is used. So there's a really concrete question I can ask related to this, which is if I have more than one bubble, should I expect those bubbles to cluster together or not? Are they correlated in any way? It's very difficult to answer that question with the kind of existing formalism. But just to give you a bit of a spoiler, here I'm showing a simulation image from this really nice paper that was led by Dalila Pirvu, who was a PhD student at the Perimeter Institute, which shows that indeed it does look like, statistically, on average, the bubbles like to cluster together. So I think this is a really neat illustration of a, qualitatively, a physical effect that is not captured by the existing theoretical tools that we have. So for me, this motivates going beyond the existing formalism and trying to generate some new insights and some new understanding in real time rather than imaginary time. And there are two ways of doing this. So the first, which is going to be the main focus of the talk, is building these quantum analog experiments. So these tabletop experiments which simulate the dynamics of a relativistic scalar field undergoing vacuum decay. But I think this method is particularly powerful when it's used in tandem with these real-time lattice simulations, which I've already shown you a couple of results from. And towards the end of the talk, I'll be telling you a bit more about that simulation method as well. Great. So that's the kind of goal of what we want to do and how we want to go about it. But I'm going to now flesh out, just kind of sketch the broad brushstrokes of how you could build a analog experiment in the laboratory that would capture this process of vacuum decay. And the first thing I want to emphasize is that this isn't just a complete pipe dream. This is something that is actually in progress at the moment, and we're getting increasingly close to having an analog experiment that will be able to do this. So it's being developed by the team led by Zoran Hadzababic at the Cavendish Laboratory in Cambridge. So these guys are world-leading experts in these cold atom experiments I'm going to be telling you about. And for them, this relies on existing experimental know-how, so existing techniques that they have, and it's really just applying it in a new way to simulate the early universe. So yeah, stay tuned for the experimental results that will be coming out, hopefully in the coming months. So the experimental platform that we have is ultra cold atoms. So you have a bunch of atoms which behave like bosons. And if you cool them down to ultra low temperatures, they want to undergo Bose-Einstein condensation. And the key thing is that the many-body wave function that describes this condensate is a quantum field which you can control in your laboratory, and it's macroscopic. So it's large enough you can take pictures of it. So we have a quantum field we can take pictures of, and the goal will be to try to get it to form bubbles. So this field obeys this equation I've written down here. This is very similar to the standard Schrödinger equation. We have this non-relativistic type kinetic term. We have some kind of potential, which I'm going to set to 0 for now, and I'll come back and mention that later. But the one difference from the Schrödinger equation is I have this extra term, which goes like mod psi squared, which captures nonlinear interactions, so due to different atoms bumping into each other, basically. So this is how you can tell the difference between having a single particle wave function and a many-body wave function with typically, something like 1,000,000 atoms in it. Okay, very good. But this equation looks nothing like the Klein-Gordon equation I wrote down before. And there's no kind of potential with local minima and global minima, which is crucial for vacuum decay. So how do we get from this to vacuum decay? Well, the first hint that there could be something useful here comes from looking at the dispersion relationship for excitations of this condensate. So on small scales, I get this behavior where the dispersion relationship is quadratic, which is exactly what you expect from just the Schrödinger equation. So this is the hallmark of something looking non-relativistic. But if I zoom out and I look on large scales, so the long wavelength modes in the condensate, these have a linear dispersion relationship. And the really nice thing about this is that makes these excitations look relativistic. So this is exactly the dispersion relationship you would have for a massless relativistic field. And so here the proportionality constant in that relationship looks like the speed of light. In fact, in this condensate, it's the speed of sound, but this is going to play the role of the speed of light in the analogy. So, okay, that means that we can say something about a massless relativistic scalar using these condensates, but I don't want a massless field. I want a field which has a potential, which has a false vacuum and a true vacuum. So the way to add a potential in is to have not just a single cloud of atoms, but two clouds of atoms that are sitting in the same place in your lab and are coupled together. They can talk to each other. So concretely, this would normally be something like, two different hyperfine states of the same atomic isotope. And so if you shine a coherent light on them with the correct frequency, you induce transitions between these two states. And that means that your two clouds are talking to each other. And you can show mathematically that this causes if I look at the relative phase, so the phase difference between the two wave functions for the two clouds, this induces a cosine potential between those two. And this is very easy to understand because if I put the two clouds, the two wave functions out of phase with each other, well, the fact that they can talk to each other means that there's an energy cost associated with that. So then you're sitting at the top of this potential. Whereas if they're in phase with each other, you're sitting at the bottom. They like that. It's a lower energy state. So, okay, great, but that doesn't allow me to have vacuum decay, right? Because if I start at the top of the cosine, I'll just drop straight down to the bottom. There's no first order phase transition, there's no bubbles that are created. So really what I want to do is create a local minimum at the top of that cosine. And it turns out the way to do this is to take that coupling, right, that coherent light that I'm shining that couples the two clouds together, and to rapidly modulate it in time. And this is not super intuitive, but there's a nice comparison we can make with a classical pendulum. It turns out that the mathematics is exactly the same. So a classical pendulum has a cosine potential. If I put it in the upward position, it wants to drop down. So it's just unstable. But if I rapidly modulate the pivot point of the pendulum, I can stabilize that upward position and I can even prod it a little bit and it will stay stable. And it's only when it makes a large enough deviation that it discovers that it wants to drop down. And that's being illustrated in this little GIF here. So what this means is that if I modulate the coupling between the two clouds, I create effectively a scalar field with a local minimum in the antiphase state and a global minimum in the in-phase state. And so I get this nice periodic potential with false vacua and true vacua, which is exactly what I want to see, vacuum decay. So now if I go back and I compute the dispersion relationship again, I see that I get exactly what I want. So again, on small scales, unavoidably, this thing is made out of atoms. So there will be some non-relativistic behavior if I zoom in on small enough scales. But if I think about in the IR, a kind of effective theory describing the long wavelength modes in this condensate, or this pair of coupled condensates, this looks exactly like the dispersion relationship for a massive Klein-Gordon field, where this mass is set by the curvature of the potential around the false vacuum. So that is exactly what we would want to see. And in fact, the statement is even stronger than that. So this really is just saying something about small fluctuations in the false vacuum. But I can actually do a much more complete calculation for arbitrarily large changes in this phase field. And it obeys exactly this Klein-Gordon equation if we're in the right experimental regime. So this is really exciting because it means you can create a system with a degree of freedom that behaves like a scalar field in a false vacuum potential. So that's the kind of sketch of the proposal for how to simulate this thing in the lab. You create this system with this degree of freedom and you watch what it does and you take pictures of it. So I'm now going to describe some of the theoretical work that I've been doing to try to understand this analogy in more detail and to kind of prepare the way for the experimental data that's coming. And the main tool that I and my collaborators use for this is these semi-classical lattice simulations. These are real-time simulations, and I've already shown you a couple of simulation outputs, but just to describe in a bit more detail what these are actually doing. So in the standard Euclidean imaginary time picture for calculating, the rate at which these bubbles are expected to form, what is usually done there is you start from a kind of classical looking state. You ignore any fluctuations in the field. You just say it's homogeneous everywhere. And then you take a very non-classical path in imaginary time and you end up with a bubble. Okay. And this is one way semi-classically of approaching describing how these bubbles form. What we're doing here is kind of conceptually the opposite of that. So we put all of the quantumness of the problem into the initial conditions. So rather than having a homogeneous initial state, we draw realizations of the vacuum fluctuations in the field. And then if you just take that and evolve it forward in real time using the classical equations of motion for the field, what you see is that the fluctuations interact with each other non-linearly and eventually you form bubbles. But in this case, they'll look like kind of noisy, perturbed bubbles because there are fluctuations in the system. Now, this isn't something that we just invented. This is a well-known approach, particularly in the kind of quantum optics, atomic physics community, where it's called the truncated Wigner approximation. And you can show that semi-classically, this is a self-consistent way of approximating the dynamics of the field to leading order in H bar. So these two methods are kind of different semi-classical ways of trying to describe the same process. So that was a lot of words, but I'm now going to show you some videos which are going to try to summarize the kind of the current state of the analogy. So what I have is on the left-hand side, I have a 2D lattice simulation of the analog system that I described to you before. So these two clouds of atoms with this coupling that is being modulated. Whereas on the right-hand side, I'm using the same simulation method, but I'm just simulating the Klein-Gordon equation. And what you can see is that in both cases, I form a bubble, the bubble expands relativistically, and eventually there are some collisions and some dynamics that happens. But I think this shows quite clearly that there is a really strong analogy here. There are some interesting kind of more fine-grained differences. And this is related to, well, we believe it's related to questions about renormalization, which maybe we can, if people are interested, I'm happy to answer questions about that on the Mattermost. So what are the kinds of observables we can extract from these simulations? Well, one thing that you would want to do to make contact with the kind of existing Euclidean formalism is to calculate decay rates. And the way that you would do this in the simulations is you run a very large ensemble of simulations. Each of them will form a bubble at a different point in time. So that's kind of shown by these different tracks in this diagram here. And what I can do is I can just count the times at which the field decays in all these different simulations. And this allows me to draw curves like this, which track the survival probability of the field as a function of time. And what we see is that in each case that I've simulated, so each different colored curve here is a different ensemble with different physical parameters. But in each case, we have this really nice regime of exponential decay, which is exactly what you would expect for a constant decay rate. So these straight lines are what we expect to see. What's more is that I can look at the slopes of these lines that tell me about the decay rate and ask, okay, do those slopes vary in the way that I would expect with the physical parameters? And the answer is yes, they do. There is one puzzle at the moment, which is that the overall normalization of this rate, it's significantly faster in the simulations than what you would calculate from just the simplest version of the Euclidean calculation. And we have some ideas for why this might be the case, which maybe again can be unpacked in a discussion session. But this is just to show that this is how we can make contact between the two different approaches. So before I wrap up, the one final thing I want to say is something I think is really, really exciting about both the simulations and the analog experiments is they don't allow us just to compare with the Euclidean results. They allow us to go well beyond the Euclidean formalism and to answer completely new types of questions. So the simulation output that you get, I think, as you can see from the videos, is much more kind of dynamical and rich in information. And you can see all kinds of interesting things like precursor events. So these kind of oscillating blobs of scalar field that turn into bubbles, and also peculiar velocities of the bubbles. There's all kinds of things that we can extract from the simulations, and I'm really excited to work towards, observing these things in the experiment and hopefully gaining some new insight into the physics of vacuum decay in the early universe. Okay, so I'm pretty much out of time. I'm going to wrap up there. But essentially, I just want to emphasize that vacuum decay is ubiquitous in early universe cosmology, but is relatively poorly understood. And that these analog experiments, I think, are a really exciting way forwards for trying to understand them better. So thank you very much for listening.